part of the class, or see it again if you missed part of it. If your internet drops out and back at some point, you are more than welcome to do so. It'll be posted on the Google Classroom right after class tonight. Alrighty, so here we are at the very end of week 1, Thursday, April 8th. So just a reminder, in case you haven't gotten to it already, the assignment that got posted today was the writing sample that I'm hoping you guys get a chance to send in. So like I was saying, on Tuesday, right around now is when the Excel Center is kind of wrapping up this big drive to collect writing samples from a bunch of students and kind of use those to look at how students do with their writing over their time here at the Excel Center. And so because of it, for this Thursday assignment, I'd really appreciate it if you could take a couple minutes, maybe even after class ends today, because I don't think we're going to be going the whole time, and write maybe like a page or so on a piece of notebook paper like this one about any sort of experiences you've had with science classes, either here at the Excel Center or in like your past career. Yes, Takesha, you got a question for me?
You just answered it, because I was going to say I never took classes with the Excel Center for Science.
All right. Yeah, I figured that'd probably be the case for a couple people. And so you can also write about either past science classes or things you're interested about learning either in this class or in future science classes here at the Excel Center. Like, what are some science things that you think would be really cool to learn about? And so handwrite this down on preferably about like one full page. We just want to make sure that there's enough writing on there so that we can kind of get a good sense of your writing ability. So somewhere between half a page to a page would be great. And the two things really make sure to remember to do, Guillermo, good to see you, is please make sure that your full name, first and last name, fully spelled out, and the date are at the top of the paper. As teachers, we can't send it into the Excel Center unless it has both of those things on it. So if you send it in with one of those things missing, I'll send you a note reminding you to put that on there, take another picture, and send it to me. So once you got your writing written down and your name and date on it, just take a picture with it on your phone, and then you can either email it to me, text it to me, post it on the Google Classroom, whatever works best for you. Dang, there was something else that I was going to say about it, and now I don't remember what it was. So obviously, since you guys are all here in class right now today, you all earned your attendance credit for today. So if you don't get around to doing this until sometime on Friday or over the weekend, that is okay. But if you could get it turned into me at some point in the next few days ago, I would really, really appreciate it. Again, we're not going to be like critiquing you on this or giving you a grade or like looking at your grammar or spelling or anything like that. We're just gonna kind of look at it in a very broad sense and use it to compare to maybe some of your old writings or some of the other people kind of in your grade level to see where everybody is in their writing. Alexandra, even if you show up late, you can still get counted for attendance, and you can still turn in this assignment later if you're not able to get to it today. As long as you get it turned in at some point, that is the main thing that I'm looking for. All right. So that is kind of the little first piece of business that I wanted to get out of the way there. So moving on to kind of the main thing that we're talking about tonight. Again, just to kind of get everybody's science brains going, get you ready to start kind of thinking about this stuff as we move forward in this class. the first thing that I want to go over with you guys is called the scientific method. It's essentially sort of a list or guideline of steps that scientists follow in order to create good experiments and come up with good answers to the questions that they have about the natural world. So it's a series of steps that scientists use to make sure that they're doing everything correctly so that they can create sort of the best information, the best data possible in order to answer the questions that they're really interested in. So no matter what types of scientists you are, you're following the same sort of basic series of steps. So today I'm just going to kind of take you through a brief tour of each one of these steps, what it means and how scientists use it. And so before we get into it, I wanted to kind of give you an overview of some of the stuff that we're going to be talking about. So it all starts with some sort of observation, some sort of thing that the scientist notices about the natural world that they're interested in. This generally leads them to a question, something that they can ask about what it is that they have observed. And they use that question to come up with their hypothesis, which is like a best guess or best prediction about what they think the answer to this question could be. They then have to design an experiment in order to test that question, test that hypothesis, gather some data, gather some results, some observations about what they are testing, what they're doing the experiment on. And then finally, they can use that data in order to reach some sort of conclusion, some sort of final answer about whether or not their hypothesis from the beginning was right or wrong. So this is sort of the main series of steps that scientists will go through when they're trying to develop some sort of question and then answer it about something in the natural world. Again, science is all about studying the world around us. That could be from giant like planets and galaxies out in space down to the tiniest little microbes and microorganisms that live on planet Earth. But if you're trying to answer questions about things happening in the natural world, scientists have found that the scientific method is a really, really handy-dandy way to go about doing that. So the main thing that we're going to kind of do today is walk through these steps one by one, talk about what goes into them and how to make it a good scientific experiment. So it all starts with some sort of observation, something that you gather through your senses about the world around you. Now, for the most part, when people hear the word observation, they think about seeing things, right? If you observed something, that means that you saw something happen. And that's true. A lot of good observations are made through seeing. That includes taking things like measurements and stuff like that and counting things up. But sight is not the only way that we observe the world around us. We actually use all 5 senses in order to observe the natural world. So yes, you can see things, but you can also hear things in your observations, right? You can hear if something is really far away or really close, if it is coming from the right side or from the left side, if it is really loud or really quiet. All those different things are things that you can observe even with your eyes closed just by listening and hearing. You can also observe things.
Sorry.
Yeah, go for it.
No, I'm just joining in. Sorry.
No problem. Thanks for being here. Appreciate it. So you can see things, you can hear things, you can touch things. So your sense of touch is another one of your senses. Like I can touch my desk and my computer and feel that they're really smooth and hard. And then I can touch my paper over here and it's also very smooth, but it's very kind of wibbly wobbly, it's very flexible. Right, all these things I can sense even when my eyes are closed using my sense of touch. You can also observe things through smell. So you can smell if things smell really good or really bad. if there's like a really strong smell close to you or a really faint smell from somewhere in the room. And then finally, you can use your sense of taste to make observations as well. So hopefully you're mainly doing that with food and not putting other things in your mouth, but things like sweetness, sourness, if something is really crunchy or something is really chewy or gummy, all of these things are things that you can observe about food even after it goes into your mouth. So with observations, you're using all five, up to all five of your senses, I should say, and you observe something about the natural world, something that if you want to think about it scientifically, maybe gets you interested, sparks your interest, makes you start to wonder what's going on here. So an example that I'll kind of be going back to as we go through these notes to kind of help you guys think about some of these steps is imagine that you're going on a walk through like a park somewhere nearby or through like a nice greenbelt area of Austin. And there's all these little ponds around, and a lot of the ponds have little salamanders in them. And salamanders, if you don't know what those are, they're like lizards that like to live by water and ponds and lakes and stuff like that. So these little lizards, these salamanders, like most lizards, they're supposed to have a nice, long, straight tail. That's kind of the default tail shape for lizards and salamanders. But in a couple ponds, you notice that the salamanders in there do not have a nice straight tail. Instead, they have weird, curvy, bendy tails. So you're like, oh, that's weird. They're not supposed to look like that. They're supposed to have nice straight tails. I wonder what could be happening that is creating these weird tails in these salamanders in my woods. So that sort of observation would start you to get questioning, which would lead you to your hypothesis. So a hypothesis is essentially a fancy kind of scientific way of saying a guess or a prediction about the observation that you made. So a suggested solution to some sort of problem that you have encountered that you're trying to solve. So you see these salamanders with the crooked tails, and you might come up with a hypothesis about why it is that their tails look so weird. A couple important things to remember about a hypothesis is that it must be testable, meaning that your hypothesis has to be something that we can do a scientific experiment on and gather data in order to answer the question, right? So some examples of non-testable hypotheses, which is the plural, would be something like, oh, these salamanders have crooked tails because the gods of this lake have decided that these salamanders should be different from the other ones. Cool, that's a really great guess as to why they have weird tails, but we can't really test if the sea gods are creating crooked tail salamanders. Another not testable hypothesis would be, oh, well, these salamanders were born on June 23rd, which meant that Venus was in its aspected phase, Mercury was rising, and the dog star Sirius was in the northwest quadrant of the sky. So all of those things interacted with each other and created these salamanders with the weird tails. Again, that's a totally fine thing to guess about why the salamanders have tails that are messed up, but you can't really do a test on if the positions of the planets and the stars are affecting their growth. You can't really change their position and see if that causes any changes, right? So in order for a hypothesis to be good, it has to be something that we can test. One good way when you're kind of starting out writing a hypothesis to kind of phrase it is as an like an if-then statement. If I do some sort of test, then this is the result I think I'll get. So if your question was about like, I don't know, a super simple example, like fertilizer for plants. You wanted to know if this fertilizer that you bought is actually going to help your plants grow. Your hypothesis could be something like, if I add fertilizer to my plants, then they will grow taller and prettier than the plants that did not get any fertilizer. So if I do some sort of experiment, then this is what I think the results are going to be. So a hypothesis kind of works like a prediction. You're predicting, you're guessing what you think your results will be based on some sort of test that you're going to do. So our hypothesis, our scientific guess, our scientific prediction, what we think is causing this problem that we have observed. So, for example, you might hypothesize that the reason the salamanders in the pond have weird tails is that they grew up in an area with lots of pollution. There's some pollution in their water and soil, and that was causing them to have weird tails. If you wanted to frame it as like the if-then statement, you could say, if salamanders grow up in a polluted area, then they will develop weird, bendy, curvy tails. So that is our hypothesis. That is our best guess, our best prediction about why our salamanders don't have nice, long, straight tails. All right, I know that hypotheses can be a little bit confusing the first time you hear about them, especially it's a big, long, confusing, fancy science word. But does anybody have any questions so far about what a hypothesis is or what scientists use hypothesis for?
No, sir.
No, sir.
Right. You are a scientist. You have observed these salamanders. You have hypothesized that maybe it's pollution that is causing them the bendy tails. Yeah, Alejandra, go for it.
Oh, no, that was my mistake. I'm sorry.
No worries. Happens to me all the time in meetings. Hey, Kimberly, no worries. Thanks for being here. So you're a scientist. You saw these salamanders. You hypothesized that maybe it's pollution that is causing them to grow up with weird tails. But as a scientist, you want to prove it. You want to find evidence. You want to show that pollution does cause these problems in salamanders. The best way to do that is to run an experiment. So an experiment is a procedure that a scientist does in order to test out their hypothesis, to see if they can gather data, gather information that will show their hypothesis was right. So we want to figure out, was our guess right or was our guess wrong? And the way that we can do that is by designing and running a good experiment. So there are a couple things that go into designing a good experiment that will give you good answers about your question and your hypothesis. One of the big things that you want to do at the start of your experiment is figure out your variables. So variables are factors in the experiment that can change, things that can affect the outcome of your experiment. And so in a little bit, we'll break down kind of what the major categories of variables are. For now, one of the big things to know about these variables is that if you want to design a really good scientific, a really valid scientific experiment, you want to have only one variable that is changing, only one thing that changes from one of your groups to another group. So in order to kind of show why this is, I'll give you guys a little bit of an example. Let's say that you want to do an experiment that will show pollution causes salamander tails to grow weird. So you set up two different chambers, two different like environmental ecosystems. In one, you keep it at a nice 77 degrees, 80% humidity. There's plenty of water in a pond and the soil for the salamanders to live with and you keep it clean of any pollution. In the second tank, the second chamber, you cool it way down. You set it at maybe 60 degrees. You take out a lot of humidity. You make it very dry, very limited water resources available. And you add in some pollution to the water that's there and to the soil. So you run your experiment in your warm, wet, humid, pollution-free room and your cool, dry, arid, pollution-filled room. At the end of the experiment, you see that room number 2, with the cooler weather and the no water and the pollution, has salamanders with a bunch of crooked tails. And room number 1 has salamanders with a bunch of normal tails. Based on this experiment, where one room was warm and wet and no pollution, and one room was cold and dry and with pollution, can you say for sure that it was the pollution that caused the weird tails in the salamanders? Think about it for a second and then feel free to answer either out loud or in the chat. All right, Annalisa thinks yes. Anybody agree with her, disagree with her? Do you think that you can say it was definitely the pollution that was causing the weird salamander tails in that experiment?
I agree too.
Elliot agrees. All right. So, interesting. All right, so we have these 2 chambers, and there's lots of things different about them, right? And so, yes, there is no pollution in one and pollution in the other. And we thought that's what would cause the difference, and then the difference happened, and so it seems like our experiment is proven, right? It seems like our hypothesis is supported. However, if you look at the experiment again, yes, the pollution was different in the 2 different rooms, but what if temperature affects how salamander tails grow? What if water affects how salamander tails grow? These things were also different in the 2 different rooms, right? So because there is so much difference between the rooms, we don't know 100% for sure that it was the pollution that was causing the problems with the tails, right? Maybe something about growing up in a dry environment will cause the tails to grow weird and curvy. Maybe something about growing up in a cold area causes the tails to grow weird. Maybe a combination of the cold and the pollution is what causes the tails to grow weird. We don't know for sure which one was the main cause of the tails. We just know that something about that second room caused the increased problems in the tails. So in that version of the experiment, we had too many changing variables, so we didn't know which one was going to be the one that affected the tails. Now, if we go back and do that experiment again, and let's say this time, both chambers are at 77 degrees. Both chambers are at 80% humidity. Both chambers have plenty of water. But the only thing that we changed is that one is pollution-free and one has pollution added to it. If we do that experiment and still get salamanders with crinkly tails in the pollution chamber, then we have a lot more evidence, a lot stronger case for it being just the pollution that is causing the problems in the salamander tails, right? Because that was the only thing that was different between the chambers. The temperature was the same, the humidity and the water were the same. Only the pollution was different. And yet we still had the differences with the salamander tails. So by only changing the one variable of pollution being there or not there, we were able to really clearly see that it was the pollution that was causing the problem. If we had the first experiment where we have all of those different variables, the different heat and temperature and humidity and stuff like that, it makes it a lot harder to say which one is the best or is the most cause of the outcome, the most cause of the tails. We can't say for sure. Maybe it's something, a little bit of the temperature and a little bit of the water and some of the pollution, but we don't know for sure. So in order to have a really good experiment that has really the clearest results that we can get, we want to try to make it so that there's only one thing that is different between the two groups. That way, if they grow differently or do something different, we can say it has to be that one thing that we changed. All right. Everybody feel kind of okay with that? Does that make sense to everybody?
Yes.
Yes.
Yep.
All right. Cool.
Yes.
Awesome.
Yes.
All right. So by
Yes.
only changing that one thing, we're making sure that if some sort of result happens, that result has to be due to that one thing that we changed. So changing that thing and measuring that thing are examples of variables, things that occur or that can affect the outcome of the experiment. So generally, in a really good scientific experiment, you have that one variable that changes, so that one thing that we're changing between the two experiments. And then you have the thing that you're observing or measuring. So with our salamanders, we're changing if they have pollution or not. And then we're observing how many salamanders grow up with crooked tails. So we're changing one thing and then measuring our results, observing our results. So these are our first two major groups of variables. The first one, that variable that is changed, is called the independent variable. So the independent variable is the thing that we, as the scientist, as the experimenter, are changing. It usually is at the very start of the experiment, we decide this group is going to do one thing and this group is going to do something else. This group is not going to get any pollution. This group is going to get pollution. This group of plants is not going to get any fertilizer. This group of plants is going to get fertilizer. Those are examples of independent variables. The one thing that the scientist is changing in their experiments. So on the opposite side of the experiment, at the end of the experiment where you're counting or measuring or observing things, those are called the dependent variables. So whatever you're measuring or observing over the course of the experiment or at the end of the experiment is the dependent variable. So any sort of measurement that you take or any sort of count that you do of your experiment is a dependent variable. So for example, how many salamanders grew up with crooked tails? The number of crooked-tailed salamanders is a dependent variable. how tall the plants grew when they had fertilizer added to them, or how tall the plants grew in our fertilizer experiment, or maybe how big they grew, or how many leaves, or how many flowers they grew. Counting those things up would be our dependent variable. So it's called dependent because it depends on what you do with the independent variable. So our dependent variable, the salamanders with crooked tails or the height of our plants, depends on how you change this independent variable. So we have our independent variable, which is usually at the start of the experiment. It's the thing that we're changing, what the scientist is affecting at the very beginning of the experiment. And then our dependent variable is at the end of the experiment. It's what we're counting or measuring or observing as we go through the experiment. So the dependent variable is like our results, our data, what sort of information we are gathering as the experiment is going on. So independent is what we're changing. Dependent is what we are measuring. So those are kind of two smaller sets of variables. And then one big set are known as control variables. So control variables are things that the scientist is controlling or keeping constant, keeping the same across all of the different experimental groups that they have. So we don't want control variables to get in there and affect the outcome of the experiment. We don't care about these ones. We want to know about the independent variable. That's the one that we're changing. So the control variables, we want to try our best to keep the same over all of our different groups. So in our salamander example, we would control the temperature and the humidity and the amount of water. Those would be control variables for that. Things that we want to keep the same between the different groups so that we could tell if pollution is having an effect. Similarly, if we had that fertilizer example with our plants, control variables would be things like how much sunshine does the plant get each day? How much water does the plant get each day? What type of soil is the plant being put in? What type of plant are we using? What type of pot is the plant being put into? All of those things you would want to keep the exact same across all of the different groups in your experiment. So some plants are in your no fertilizer group, some plants are in your fertilizer group, but all of them should have the same amount of sun, the same amount of water, the same type of soil, the same pot that they're put into. That way, only the fertilizer is affecting their growth. We don't want any of these control variables to be affecting how these plants grow. We want to make sure they're all put in the exact same conditions so that only the fertilizer is affecting the outcome, not the sunlight or the water or the potting soil or anything like that. So control variables are things that we keep the same over all of our experiments. We keep them controlled and only change that one independent variable. So again, we're not testing our controls. We don't care about how the sunlight or the temperature or the water affects the lizards or the plants. We want to know about other things. So instead, we keep them controlled for comparison. If everything else is the same, it makes it easier to compare your groups that have the different independent variable. It's a lot easier to compare your pollution and no pollution group or your fertilizer and no fertilizer group if all of the other control variables, if all of the other controls are the same. So that's why we want them in there, so that they don't affect the outcome of the experiment. And we know that our results are only due to that independent variable. All right, so to make sure that everybody is kind of on the same page when it comes to these different types of controls and variables, I'm going to set up a really basic type of experiment for you guys, walk you through the different steps, and then I want you guys to tell me a little bit about what our independent, dependent, and control variables could be for this experiment. So let's say your question is, what is the fastest way I can get from school to my house? So obviously we're gonna assume that we're way back in the day, back in normal times, pre-COVID times. Everybody is coming to school on the same days and going to class and stuff. So you're at school on a regular basis. And normally you have this one way that you get home from school. I think in the example it says walk, but most people here, I know, drive or take the bus or walk or do some sort of combination of the three. So we'll just say drive to make it easy. You're driving from the school to your house. You have this one way that you always go. It seems like the easiest way. But what if there's a faster way? What if there's a better way out there and you just don't know about it because you haven't tested it yet? So you want to try and figure out what is the fastest way to get from school to my house. So on Monday through Thursday, you decide every day I'm going to do a different route home. I'm going to change how I get home from school. On Monday, I'll take route A. On Tuesday, I'll take route B. On Wednesday, I'll take route C. And on Thursday, I'll take route D. So every day, I'll change how I get home. I won't go home the exact same way twice. You also, in order to figure out which one is the fastest, you're going to time yourself. So as soon as you climb into your car at school, you're going to hit the stopwatch button on your phone. And as soon as you climb out of your car, when you get home, you're going to hit that stopwatch button again and write down how long it took you to drive from school to your house. So this is specifically for you. You want to know that when you are driving, what is the fastest way to get home? So you're not going to ask any of your friends to like drive this route with you or do it for you, because you want to make sure that you are the one that is doing all of this timing. So you're going to be the same person driving it every day. You also are going to make sure to drive the same car every day. So every day you're going to take your car. You're not going to borrow your mom's minivan on Tuesday and your brother's sports car on Wednesday and your uncle's motorcycle on Thursday. You're going to drive the same car every day. You're going to leave school at the same time, since you get out of class every day at the same time and you go straight home. So you leave school at the same time every day, and you always start at school and you always stop at home. You don't stop anywhere in between. You don't pick up dinner or go grab a smoothie or like some ice cream or something on the way home. You always start at the school and drive straight home. So you're seeing, of all of these different ways that I can take to get from the school to my house, what is the fastest way? Which one is going to get me home faster? So I want to know what you guys think about our different sets of variables. So we'll go ahead and start off with the independent variable. So in this driving from school to home example, what is our independent variable?
Me,
Whoever.
myself.
Quite.
Is
Because
that the part
remember,
that doesn't change?
so
Or the,
self is a part that doesn't change, but that is not what the independent variable is.
It would be the different ways you travel to and from school that you choose.
Mm-hmm. Guillermo has got it perfectly. So remember, our independent variable is the thing that the experimenter is changing. It is what we are doing different in each experiment. So like Guillermo said, in this case, we're changing how we get home from school, right? We're taking different routes on Monday, Tuesday, Wednesday, and Thursday. So the way we are getting home is our independent variable. That is the thing that we are changing.
Oh, I got it confused with the dependent or variable.
So speaking of, if changing up how we get home is the independent variable, what is our dependent variable?
Me?
The time.
Anybody? What was that? So I think somebody said it.
The time.
The
Yeah,
person.
exactly. The time, precisely. I think Lorena had it a little bit earlier as well. But yeah, how long it takes you to get home is the dependent variable. Because remember, dependent is the thing that we are measuring. It is what we're observing or counting as part of our experiment. So we're changing how we get home, but we're measuring how long it takes to get home, the time that it takes to get from school to our house. So those are our independent and dependent. What about for people not named Guillermo? What are some of our control variables? What are some things that we are keeping the same across all of the experiments?
What you're driving?
School and home. School and home.
So we're driving the same thing, same car. We're starting and finishing at the same spot. We're starting at school, finishing at home. Very good. Any other control variables? Any other?
Maybe like the speed, right?
Or
no?
Kind of. I mean, you could say that having yourself be the driver every time, right? So you're going to drive the same way every time. Like, I'm sure you all have some friends that are like super aggressive, scary drivers, and some friends who are like frustratingly slow turtle drivers. But you are going to be the driver each time. And so it's not going to be affected by the person who is doing the driving, because you're going to drive with your same instincts and your same style of driving each time. Exactly. Those are all really good control variables. So starting and finishing at the same spot, driving the same car, having the same person be the driver each time. I know somebody in my other class mentioned that you're leaving from school at the same time each day. So hopefully you should, I mean, in Austin, who knows, but hopefully you're hitting kind of the same amount of traffic each day. So it's not like some days you're leaving at 9 a.m. and some days you're leaving at 2 p.m. and other days you're leaving at 9 p.m. You're leaving at the same time each day. So all of those are really great examples of control variables. This one still has the walking as the one, so they say the same walker, which is like the same driver. But yeah, all the ones that you guys mentioned were also really good control variables. So we have our independent variable, which is what we as a scientist are changing. We're changing how we get home from school. We're changing if the plants get fertilizer or not. We're changing if the salamanders are in the pollution or no pollution group. What we're measuring is our dependent variable. We're measuring how long it takes us to get home. We're measuring how tall that the plants grow. We're measuring the number of salamanders that grow up and have crooked tails. All of these are dependent variables, things that we are measuring in the experiment. And then finally, we have our control variables, making sure that we have the same person driving home in the same car, going from the same starting and ending point. We want to make sure that our plants have the same amount of sunlight and water and are in the same types of soil and the same pots. We want to make sure that our salamanders have the same temperature and the same humidity and the same amount of water in each room. So things that I want to keep the same, keep constant across all of our experiments, these are our control variables. All right, thank you guys so much for your help with that example. Does anybody have any questions about setting up an experiment, independent versus dependent versus control variables? Anything that we've talked about so far that you still want a little bit of explanation on?
No, sir.
No.
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 All right, sounds good. So finally, a couple things that come up in the scientific method. You've set up your experiment, you've made sure you have one independent variable, you know what you're going to measure, you kept all of your controls stable. Now it's time to gather your data. So your data is the results of the experiment. It is basically what you are measuring for your dependent variables. So number of salamanders, plant height, time to get home, that's your data. It can come in two different forms. Quantitative, which is the one that it generally is, and that means a direct number. So the plant grew 14 inches. It took me 327 seconds to get home. There were 23 salamanders that had crooked tails. All of these are quantitative points of data because they are described by numbers. You can also have qualitative data, like if something changes color in your experiment, it goes from purple to yellow. That's something that you can observe, and that's a result that you can have, but you can't really express that in a number. It has to be some sort of description. Same thing with if you're like describing how things smell or how strongly things smell or how things taste. You can't really put a number on how bitter something is. And so it's more of a descriptive or a qualitative type of data. So you've run your experiment, you've gathered up all of your data, you sit down and you analyze it, and you use that data and that information to reach your conclusion. So in a conclusion, you're using the data you got from the experiment in order to answer your hypothesis. Either yes, my hypothesis was supported, we had more salamanders that had crooked tails in the pollution room, or no, my hypothesis was not supported, we ended up having the plants that had fertilizer grew the exact same as the ones with no fertilizer. So in general, a conclusion, like a good conclusion, has two parts. There's a part where you clearly state your final results. So what did you find in your experiment? What were your final dependent variable measurements? And you say whether or not you supported your hypothesis. So you basically say, I was right with my hypothesis, or I was wrong with my hypothesis. I thought the pollution was causing the problem with the salamander tails. I did my experiment, there was no difference, and so maybe it is something else in their environment that's causing that problem. So you gather up all that data, you take all those measurements, and you use those measurements to define your conclusion, your final results that either support your hypothesis or don't. So one important part of the scientific method that I like to bring up, because it often goes overlooked, is the need to do multiple experiments and multiple tests of the same experiment. And that's because if you do one experiment one time on one salamander, you don't really have a lot of strong evidence for your results. So in order to make sure that you actually do have good, clear results that support your hypothesis, it's a good idea to do multiple different groups of your experiment, or your experiment multiple times, right? If I took the salamanders and I put one in the normal room and one in the pollution room, and they grew up and the pollution room one had a crooked tail, and I was like, oh, all salamanders that grow up in pollution will have crooked tails. Doing it just based off of that one result isn't really good science. The way that I kind of like to think about this, especially in the current day climate, is think about the COVID-19 vaccine. So in order for vaccines to be approved by the FDA, the Food and Drug Administration, companies have to put their vaccine through what are called phase 3 physical trials. This is a process where they have to test the vaccine on tens of thousands of people in order to show two things: that the vaccine is effective at preventing people from getting COVID, and that it is safe and will not have very many harsh side effects in a lot of people. So the reason why they have to test on tens of thousands of people is because they want really, really, really strong data about how safe and how secure their vaccine is. Imagine if tomorrow somebody was like, hey, I heard about this new vaccine that just came on the market. If you want to go get it, I promise it's super safe. They tested it on 2 people in San Antonio, and they both didn't get COVID, and they're both fine afterwards. So the vaccine is totally safe. Everyone can use it. You'd probably be a little bit nervous about it, right? You'd be like, well, they only did it on 2 people. What if those people were already immune to COVID? Or what if they already got it and so fought off the infection already? What if neither of those people tends to have a side effect of vaccines, but if you give it in somebody else, then their right arm falls off? Just by having it on a very small number of people, it makes it so that you aren't sure if maybe there's something else that could be messing with the results. So the more what's called the sample size, the more people, the more experiments that you can run, the stronger your results will be at the end of your experiment, right? If you did that plant fertilizer experiment and you gave 1 plant fertilizer and 1 plant none, then maybe there is something that you couldn't control for that affected the plant's growth. But if you gave 100 plants fertilizer and 100 plants no fertilizer, and found that the average height of the fertilizer plants was way bigger than the average height of the no fertilizer plants, then you'd have a lot stronger argument and a lot stronger set of results showing that the fertilizer helps the plants grow. So by doing multiple different trials of the same experiment, you can make sure that you're getting really, really valid, really strong data. And the more you can do it, and the more you get your results showing up, the stronger that your experiment and that your data will be. So if we kind of put all these different steps of the scientific method together, we start off with identifying and observing some sort of problem in the natural world and your natural environment that you get interested in. You form a hypothesis about what you think could be going on. If salamanders are exposed to pollution, then they will grow up with crooked tails. You then want to test this hypothesis, so you design an experiment. You have one independent variable that you change between the different groups. You choose a dependent variable that you're going to count or measure to get your results. And you do your best to make sure that all of the other variables, all the other control variables, are kept the same between all of the groups. You do that, you run your experiment. Hopefully you have 15, 20, 50, 100 salamanders that you put through it. You collect your data about how many grow up in the non-pollution room and get crooked tails, how many grow up in the pollution room and get crooked tails. Finally, you use this data to form a conclusion about your hypothesis. You say, here's what my results were, and based on those, it supports my hypothesis that pollution causes crooked tails. I gathered a whole bunch of data from my fertilizer experiment, and my conclusion is that this type of fertilizer does not actually help these plants grow. There was no difference between the water group and the fertilizer. And then finally, hopefully you do the experiment multiple times with multiple sets of groups so that you can have really strong and really good data at the very end. So by doing all of these steps, scientists make sure that they're coming up with good, testable, interesting questions, and the data that they're gathering about the questions is leading them to the correct conclusion and to the best conclusion that they can make based on what they found in their experiment. All righty. So that is the scientific method in a nutshell. The kind of basic process that all scientists, regardless of whether they are a geologist or a physicist or a chemist or a paleontologist or a botanist, they all use the same basic series of steps in order to develop questions, come up with hypotheses, design experiments, gather data, and make conclusions. All right. Does anybody have any questions about any of these parts of the scientific method? Anything that we talked about so far tonight that you want a little bit more explanation on?
No.
No.
All
No.
right. It's like most people are pretty good with their scientific method knowledge. So again, for today, the only assignment that was posted was that writing. So again, since you guys are all here on the Google call tonight, you all got attendance credit for today. So if you don't get to it tonight, please take a little bit of time to do it sometime on Friday or over the weekend. I really appreciate it. Not only do I really like getting to read all you guys writing, but it also really helps the Excel Center and our goal to kind of help people make sure that their writing is improving over the course of time that they are here. So if you haven't gotten it turned in to me yet, if you could do that sometime on Friday or this weekend, I really would truly appreciate it. That will wrap up our notes for tonight. Make sure to come back and check in on Monday for your syllabus quiz. Will be posted up on Monday for your Monday assignment. Simple, short, 5-question quiz about just some basic information about kind of this class and the class policies and stuff like that.